So, good afternoon. I'm here to talk about, about hydrodynamic effects on Syngnathids species behavior and habitat preferences. I'm going to work here with pipefish. I'm sure, or probably we are all familiar with pipefish already, but I prefer to play this short video of a Syngnathidae stifle in a Syngnathidae dorsal meadow, just to point out that this species has shape like leaves, like the leaves, and they are mostly small, slow motion animals. Even when the predator, in this case the diver, is pretty close to the fish, it tries to stay, to be stopped and not being detectable. I mean, it doesn't escape from the diver. That's kind of what I did. Okay. This group of fishes is emblematic and really vulnerable fish group. They are vulnerable mainly because some of their reproductive, some features of their reproductive biology, and they inhabit normally vegetated bottoms, and they are especially linked to seagrass species, so to seagrass meadows. They have a really poor swimming ability, means that they are not really good swimmers in general, and their strategy is more cryptic and mimetic, both in phenotype and behavior. Their main movement mean is the undulation of the dorsal fin, and the absence of or presence of different kinds of fins is one of the traits used to distinguish between or among species. I'm going to present here the 4 species we worked with in this study. 2 of them were from the genus Syngnathids. Syngnathids tifle is this one on the left, and this one on the right is Syngnathids rostellatus. Both has caudal, anal, and pectoral fins. And the other 2 are Nerophis ophidium and Entelerus aequareus. Neither of them have anal or pectoral fins, but Nerophis ophidium doesn't have neither caudal fin. In the case of Entelerus aequareus, has caudal fin, but really, really small. We know that seagrass density modifies water flow in the meadows, but does hydrodynamics also density modify pipefish habitat choice or behavior? We designed 2 different experimental approaches to address this question, this main question. The first one was an experiment to test a stress and behavioral response of pipefish to hydrodynamics, and in the second one we tested habitat choice and behavior response to hydrodynamics. To do so, we used the Flume facility in Christineberg Marine Station in the Sven Loven Center associated to Göteborg University. This flume has a measure of 8 meters per 50 centimeters wide, and it allows us to manipulate the flow velocities and the substrate in the bottom of the flume. So for the first experimental approach, we manipulated 7 different velocities. And we did it in 2 different substrates, one independent experiment with sand and another one with a substrate of eelgrass with 150 shoots per square meter with density. I don't know, sorry. Okay, and I played these 2 videos to show you what are we measuring as behavior. In the left side, you have an Nerophis ophidium holding the leaf. In the right side, you have a Syngnathids tifle swimming. That's one of the response variables we measured in this work. And the other one was the ventilation rate. It means the opercular movement of the fish under different conditions. So what we find for Syngnathids tifle, we found that ventilation rates increases with velocity, but it increases less when the substrate was seagrass and not sand. So the interaction between both factors was significant. Flow velocity and substrate explain almost the 45% of the total variance. And regarding behavior, well, in sand they don't have a lot of options. I mean, they are resting in the zero velocity, or they need to swim because otherwise they are dragged by the flow. So the interesting part of this plot is this. And what we saw is that when velocity increases, the Syngnathids held the leaves more often. Different results were found for Syngnathids rostellatus. Again, ventilation rate increases with velocity, and it was higher in sand experiment, but the interaction wasn't significant. The flow velocity explained almost the 25% of the total variance, and there was a huge amount of the variance of ventilation rates explained by the fish ID, or the specific individual. Regarding behavior, in contrast to Syngnathids tifle, Syngnathids rostellatus doesn't seem to prefer hold the leaves when velocity increases. And now for Nerophis ophidium, we have a pretty clear response. Flow velocity increases ventilation rates in this species, and there was an obvious interaction between the substrate type and the velocity. In fact, these species were not able to deal with velocities higher than 12 centimeters per second, only one individual here, when the substrate was sand. Flow velocity explained the 30%, and substrates explained the 30% of the total variance. That was kind of expected. Nerophis ophidiots hold the leaves all the time, and especially when flow velocities increases. Entelerosa aquareus also increases their ventilation rates with velocity, and it was higher in sand, but the interaction wasn't significant. Regarding behavior, we have a pattern here different from Nerophis or Syngnathids tifle. It's more similar to Syngnathids rostellatus. This species doesn't seem to prefer holding the leaves when the velocity increases. So what can we say after this? That pipefish ventilation rate increases with stream velocity. That's kind of obvious, no? It's a more demanding energetic ambient, so the animals are more stressed and need to respond to these conditions. In general, pipefish ventilation rate increases more on sand experiments, and we found two different strategies. The swimmers, who will be Rostellatus and Entelerosa aquareus, who keep swimming when stream velocity increases, and fish fitness explain, in these two species, fish fitness explain a higher percent of the ventilation rate. That's because swimming is a more demanding activity than holding the leaves. And the other strategy will be the holders, Syngnathids tifle and Nerophis ophidium, who hold when flow velocity increases, they hold the leaves to try to stay in the meadow. And then the second experimental approach we just did it with one single species. We didn't have time enough to do the others, but I hope we can finish this work this year. We manipulate 6 different velocities, and we offer 3 different habitats: low density, high density, and sand. Same surface were offered to the fishes, and positions were swift to avoid confounding effects. And the response variables were the time spent per habitat and change in behavior similar to the previous one. What we found is that Syngnathids tifle obviously prefer to be in high density meadows, on the path in this case, not a meadow, and that they held the leaves more often when they were in the high density path. So as conclusions, we can say that seagrass meadows provide shelter for hydrodynamics to pipefish, and this shelter may be the determinant for some species, such as Nerophis ophidium. It means after some flow velocities, they will be dragged from the meadow. seagrass should density decline, and weaker low flow attenuation will increase energetic needs for pipefish and could have detrimental effects on fish fitness. And high shoot density environment is clearly preferred by Syngnathidae, and the protection from hydrodynamic exposure represent another mechanisms of pipefish fitness dependence on healthy meadows. And that's all. Thank you.
Okay, great talk, Ines. Who's got some questions? Ron.
Hi, Ines. That was a lovely talk. I was just wondering, you've got several species of pipefish, and you see different responses, and I think that's pretty interesting. Do you think that there are any functional or morphological traits that can help explain the differences in their behaviors? That's the first question. The second is that in one of the species you found that there's a lot of individual variation, that the individual itself plays a very important role. What do you think is explaining this? Because that individual behavior itself can be really, really interesting from a behavioral point of view in the context of behavioral syndromes that can be very context specific, and a tremendous amount of behavioral plasticity that it can offer a species like that.
Okay, I'll go with the first question and then I try to answer the second one. Okay. Regarding morphological features, as I present, both Syngnathids has similar morphological features, but the habitat distribution is not the same. So it's not strange that the resistance of Syngnathids rostellatus to flow velocity is higher, because the distribution is related with seagrasses and algae bottoms, but they can migrate in estuaries, and they have like a stronger swimming ability. They can move more than Syngnathidae, which is more strong, how to say that, more intensely linked to seagrass. And the other question was the inter-individual variability. This is also with Syngnathids rostellatus, and I guess this is because of what I said during the presentation, or I'm not sure if I said it. They swim more, so the difference in fitness of between among individuals will determine more the resistance to the flow velocity. I mean, if you have a fish which is have not eaten enough the last 3 days or something, and exposed to stressing conditions like we did in the experiment, his response will vary a lot, because his behavior normally will be swimming, so it's more demanding for him. And the differences in fitness, each individual fitness will be more remarkable when this behavior is the natural response. No, I don't know if I answer your question more or less. No? You can re-question if you want. Or maybe talk later.